Hello, this is Ari Everett for Professor Cody Anderson's CSC120 class in the fall of 2023. This is a demo as a follow-up to Quiz 1, and I'm going to take the quiz and show my understanding by creating different problems based off of those learning targets here. So for target 1A, it's that I can convert between unsigned binary and decimal in either direction. For this first one, I can scratch out and I will choose another number, let's say really close to it, 138 base 10. And I'm going to use the divide by 2 method. So create this table here. This will be the quotient and then remainder. I'm going to write already, before I forget, that this is the most significant bit and this is the least significant bit once we get all the answers here. So I'm going to put 138 here and then divide by 2 until I get down to the 1 of one column, which it always ends with. So 138 divided by 2 is 69 exactly and a 0 remainder. 69 divided by 2, I'm doing this on my calculator here, is 34.5. So 1 remainder here. So starting here, most significant bit, this equals 1, 0, 0, 0, 1, 0, 1, 0 in binary, base 2. And just to make sure that I can do this the other way, because that is the learning target, I'm going to convert this back into decimal by using the weighted base method here. So how I'll do that is I will start at the first digit, which is a weighted base of 0, and work my way up in their position to 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. Now I'll cancel out the ones that are zeros. So this one, this one, this one, this one, and this one, and then I'll add the rest. So 2 to the 7 plus 2 to the 3 plus 2 to the 1 equals, I'll plug 2 to the 7 in my calculator because I don't know that offhand, 128 plus 2 to 3, just to make sure it's 8, it is, plus 2 equals 128 plus 8 plus 2 on my calculator is 138. Period. And then to the right side, we do the negative bases. So that is a 2 to the negative, I think, yes, to the negative 1 here, plus 2 to the negative 2, 2 to the negative 3, and then 2 to the negative 4. So let's cancel out this one and this one. So it's 2 to the negative 2 plus 2 to the negative 4 equals 2. I'm going to do that on my calculator. And in total, this is 150.3125 in base 10 here. Okay, and moving on to P3 here, what is the largest decimal value that can be represented by 6 bits? Well, we know that binary digits is a bit, and it's 1 or a 0, so the high would be the upper value. Let's go 1, 2, 3, 4, 5, 6. Now let's convert that into decimal with the weighted base method. That equals 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 63. Okay, here's an example that I wanted to give that's not on the quiz, but part of the lesson, so to make sure I complete it, it's the divide by 2 method. You can see it here in the green box. Okay, and it'll take kind of some things that we did in the previous P1 problem, which is the opposite of the divide by 2, and then also take some principles here from to the right, where we do the fraction binary into decimal, where we take the negative weights and add them up. So I chose the number 0.52 base 10. We use the times 2 method to find what in base of 2. It's like a repeating decimal. So the more that you do this and carry this out, the closer you will get approaching to 0.52 decimal, but never getting there. So here the method is on the left, 0.52, and then you multiply that by 2, and then you have the whole number that's to the left of the radix, here, the 1, and then you have the remainder to the right of the radix, not the remainder, but the decimal form, 0.04, and then you repeat that process. So 0.04 times 2 equals 0.08, so there's a 0 here and 0.08 and repeat. I'm trying to save time and go quick because I've gone over the limit in the video and I want to make sure here. Anyway, to go quicker here, most significant bit to least significant bit, it's the opposite of the divide by 2 method, equals 100000101 base 2. Using this conversion method we used over here, it equals 0.5195312 base 10. So again, approaching that 0.52. Okay, moving along to target 1B, where we can convert between unsigned binary and octal or hexadecimal in either direction here. Let's change this to a different number to, let's say, 6316 base 8. Now it's octal, and we know that octal can be represented in binary with just 3 digits, so we want to break out these 4 into their 3-digit binary translation. So to get to 6, we use the weighted base method. So what in the 3 digits equals 6 in the weight? So I have a 2 to the 0, which is 1, and a 2 to the 1, which is 2. It's 3, and then 2 to the 2 here. So that would be, and that's 4, so I will take 110 to create that. And then for 3, This is a similar way in the way that we group it into the fours. So I'm going to remember 4 digits here to represent hexadecimal in binary. I'm going to highlight those because I can't see them very well, but I will change the number here. I'll change the last one to like 0111. This one's a little tougher because there are 16 symbols 0 to 15 that convert, and it's a little tougher to remember once you get past that number 9 into which letter is which. But let's see, 0110 is Deci 6, and so that would still translate into a 6 in hexadecimal. 1111 is all the way at the top is 15, and that translates into the very last digit of hexa, which is, or symbol, which is F, so F here. 1110 is, let's see, that's 14 deci, and that translates into A, B, C, D, E of the hexadecimal. Whew. And then 0111 is going, how does that add up to in weighted bases? That is 7 deci, and that's before the number 9, so it just stays the same from deci, and there we have our answer. And to convert back, once again, we do the same thing in knowing that 6 in the weighted bases method to convert is 0110 because we have, let's see, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Cancel those out, and that equals 6. Same thing, F, you just have to remember after 9, there's A, B, C, D, E, F. That equals the remainder decimal 10, 11, 12, 13, 14, 15 that will convert into binary. Okay, and finally we'll go down to target 1C here and convert between decimal and octal hexadecimal in either direction here. I will go do this, just do a 2405 number, and we can use 2 different methods. The longer method would be octal to binary because we know those numbers pretty easily with the weight base and then add them up based on their weighted position, or we do the sum of weights, which, let's break this out now to see how we can do that. I like the red ink a little bit better. So let's see, 2 would be to the, this is 0 position 1, 2, 3, so it would be 2 times 8, which is the base number we're coming out of, and then to the 2, and then we'll add, is 1285, and remember a base, which is deci. Okay, and the final example here is converting from decimal into hexadecimal, kind of round out the other way around here in the past 2 examples of going from a deci to hexa or octal, which you do a divide by method, but instead of 2 binary, you would do it either by the base that you're going into, which is 16 or 8. So let's come up with a new number here. We'll just do one right next to it on 7, base 10, and this is going to be, I'm going to try and make this table here. It's going to be the quotient, and then this will be deci number, and then this last one will be the hex translation to that, because I don't, those letters always kind of trip me up. And so let's convert 245197 divided by 16. 245197 divided by 16 is 15324 with a decimal remainder of 0.8125 times the denominator 16 is a remainder of 13. So we'll put that here. And then we translate 13 in decimal is going to be D, and then 12 is right before that, C, and then 13 is D, and then 11 is B, and then 3 is, of course, 3. So our answer here, going up from down from up, is 3B, D, C, D. But I'm talking in base 16.